Hello guys, welcome back to Mason African Motives. Still working on our Mechanotechnics N5 revisions as a request that we made that we are supposed to be working on the belt drives, and this is what we have. Let us just see what we're going to have in this part. April 2023 exam, question 6.1, we're given to list 4 materials used to make flat belts and V belts in this case. So for the materials, we'll be talking about the rubber, the plastic, so forth. So there are so many materials that you can actually consider in the construction or in the materials that are used to make these flat belts or V belts in this case. So we talk of leather, talk of plastic, rubber. In this case, we can just say rubber. Then also we can talk of plastic, and we can also talk of cotton or the fabric. The cotton there, we're simply talking about the fabric, and also we've got balata in this case. All right, so these are some of the materials that you can choose from in your syllabus. All right, then 6.2, we are given, this is the most important part. We need to take our information, and this question, it did a lot of things to consider. That's why to come up with this question. We have got the thickness of a 4-ply leather belt. In this case, this is a 4-ply. So it tells us about the type of belt that you are given. If it is a V belt, you'll be given the number of V belts. When you are given the ply like this, the 4-ply, like 3-ply or whatever, I mean the 4-ply or the 6-ply, whatever that you're given, it is going to be representing N, which is for the flat belt in this case. So meaning to say this question that we are working with is for the flat belt. Whatever that you're going to be using here must be of the flat belt. Remember, I've got 2 belts that you're going to consider, the V and the flat. So here we are considering a flat belt in this case. All right, that's a flat belt. So we're given a 4-ply that is N is equal to 4. All right, then we are given is a 16 millimeters thickness. The thickness is 16 millimeters. So we've got a thickness which is given by T. So 16, if you convert this to meters, that will be divided by 1,000 to be 0.016 in meters. So we've got the thickness of the belt. Then the belt transmit power. The power transmitted is the power output in this case, or the total power that you're gonna need. That is the transmitted power. So that's we've got the P out, the transmitted power of 65 kilowatts. So that's 65 kilowatts corresponding to the speed, and the pulley that is 1.5 in diameter, 1.7 meters in diameter, rotating at the speed. So we've got the diameter of 1.7, the speed of 342. All right, so this corresponds to this power, the diameter of 1.7 meters, and also the speed of 342. So that's 342 revs per minute. Take note about the units. The units is very, very important for you to consider that. All right, so we've got the speed there. Then the angle of rep. The angle of rep is the angle of contact. So we're given the angle of contact for the flat belt. We're talking about the flat belt there. So we are given the angle of contact, this one. All right, which is 165 degrees. And I told you guys, whenever you're dealing with the angle of contact, you are supposed to have this in radians. So you're given the angle of 165 degrees to radians. That's 165 over 57.3. So you're going to divide by 57.3. Thus, this value is now in radians. So whenever you are dealing with the angle of contact, in this case, you are going to work with radians. If you are talking about a condition where if you are dealing with a V belt, in this case, whereby you'll be talking about the semi-groove angle, which is beta, you have to use that one in degrees. You're going to use this in degrees in this case. But for the part of our contact angle, the angle of contact, that one is in radians. All right. So that is also the coefficient of friction between the belt and the pulley is 0.3. And we've got the density of the material. All right, let's just take 0.3 for the coefficient of friction between the belt and the pulley, which is 0.3. Then we've got the density of the material, 0.95 times 10 to the exponent of 3. Remember, density is kilograms per cubic meter. All right, so that's the density given by the symbol rho in this case. So it's just rho like this, all right? Not P, but a rho, right? So that's the symbol for density. Density, it's rho like this. This is how you pronounce it, like how it's written rho. So I don't know how you're gonna pronounce it. That is the symbol for what? For the density in this case. So we're given this density as 0.95. That's 0.95 times 10 to the exponent of 3 in kilograms per cubic meter. Remember the concept of the density related to the mass and volume, that it follows that if this is volume, this is density. So this is mass. We're going to have mass, density, volume. This is mass, and this is density, volume, MdV. So we've got if we want mass, it's going to be product of density and volume. If we want density, it is going to be mass over volume. If we want volume, it is going to be mass over density. All right, so that is what you can use. Okay, so we shall see for that. Then we are given also the maximum allowable tension exerted on the belt must not exceed. So this is the maximum tension. And this is 6.5 kilonewton per meter width, meaning to say per 1 meter width per ply. All right, we've got something that we need to consider there. All right, take note of what you're given there. So this is the maximum allowable potential, which is given as FT. So it's given as 6.5 kilonewton per meter width, meaning to say the width is taken at 1 meter in this case, per what? Per ply. So be careful on how you're going to apply this on your formulas. All right, that is the whole information that we are given. All right, that's it. So the first question was to calculate the speed of the belt, in this case, 2 marks for that. All right, the speed of the belt. So like I said, guys, this is just back to your N3. N4, I mean Mechano. So 6.21, we need the speed. And as you can see, we've got thickness this time. From the diameter and thickness and the speed, we know that we can find the speed from there. All right, remember the speed was supposed to be pi dn over 60. But because we have a thickness, we are not going to consider this. We are going to consider as d plus t, which is the thickness, all right, times the speed in revs per minute over 60 to convert to revs per second, so that our speed will be in meters per second. That's it. So that's we're just going to substitute the diameter, the thickness, the speed, right? Everything is there. So you have to check what you are given. If you are not given the thickness, you do not include this part, all right? So that's, in this case, you're going to have pi into the diameter in meters, that's 1.7, plus the thickness in meters, which is 0.016, all right, times the speed in revs per minute, which is 342. So we've got 342, everything over 60. So that's it. We're going to have our speed. If we simplify properly here, we are going to have our speed in meters per second. So that was going to give us something like 30.7285, something like that, which is 729 in meters per second. All right, so that one you are given first to calculate the speed, which is the belt, the speed of the belt, or belt speed in this case. All right, then 6.22, that is the belt mass per meter length. When you are saying per meter length, it seems like, yeah, we do not consider these things like most of the time. There's a great meaning that you are given here. We are not given the length here, guys. If you check, we are not given the length of the belt in this case, which is fine. We can calculate the mass because the mass is given this m. Let me just write it aside here. All right, 6.22. The mass m is given as the mass which is in kilograms per meter length per meter. Just like what I was explaining on the maximum allowable tension here. It's 6.5 kilonewton per meter width. What does it mean? It means the width is taken at 1 meter per each meter. 1 meter. It's here the mass over 1 meter. That is what gives us per meter, means this one over that the other one. So per meter means per 1 meter length. So the mass is given per 1 meter length. The force at the maximum, which is the maximum allowable tension, is given at per what? Per 1 meter width. So meaning to say we shall consider our width at 1 meter, our length at 1 meter per 1 meter per 1 meter width. All right. Why am I talking about? Because we are going to need this in terms of our mass, in terms of calculation. We are going to need this. Remember what I was explaining on this triangle between the mass, density, and volume. It follows that in actual sense, we are supposed to have this as, because we want to calculate the mass and we've got the density in this case. So meaning to say we are supposed to talk about what? The density. So in order for us to obtain this mass here, is going to be the product of the density and the volume in this case. So that was supposed to be the formula. We are supposed to multiply the density, which is given by the symbol rho, times the volume. All right. But the question is, all right, let's just save this. We have the density, which is fine. What about the volume? Where are we going to have the volume? In a belt concept, we are considering the area times the length of the belt in order for us to have the volume. It's a rectangular, just like a rectangular prism concept. Length length times the area gives us the volume, which is area times the length or the height. But that height, we're talking about the length. So the volume, this volume here, is simply from base area. We know that it's base area times the height. But here we shall consider the length of the belt, of which the base area, which is the area of the belt, is the product of the width and the thickness of the belt. The width times the thickness of the belt gives us the area times the length of the belt. We now have what we call the volume. So this is our volume. This is our area. So meaning in order for us to obtain this volume here from area times the length, we are going to have our formula as the width times the thickness times the length, which is our volume. This is the whole part representing our volume. This part of width times thickness is our area. All right. But this volume must be multiplied to the density in order for us to obtain what? To obtain the mass. So it's simply volume times density from this part. Volume times density. So it's like you're having a lot of things. No, it's just volume times what? Times density in this case. All right. So like I said, since the maximum tension was taken per meter width, the width is at 1 meter. So it's going to be 1 times the thickness of the belt. We are given the thickness of the belt here, which is 0.016. So we are going to have 0.016. So this is the area, width times thickness times the length. We now have the volume, and the length taken at 1 meter. Remember, we said here, this is given, the mass is given it's kilogram per meter length. Per meter length, the mass is given in kilogram per meter length. So meaning to say your length is at 1 meter. Then we're going to multiply to the density in this case of the material used. So the density of the material is 0.95 times 10 to the exponent of 3. So this will give us the mass per meter length. So our mass, if we are to simplify properly, guys, we are going to obtain 15.2 kilograms per meter length. Remember, we are taking this per meter length. Yes, the mass we're just supposed to have kilogram, which is fine, but it is being taken per meter length, so you're supposed to have it per meter like that. So you see, it's just direct application of your formulas. You just have to understand your formulas, how to use your formulas for each belt that you are working with. Let us consider the other part. They wanted us also to calculate the belt tensions T1 and T2, take note here, the centrifugal force into account. All right, 8 marks for that. The centrifugal force must be included in this case in order for us to obtain what? T1 and T2. All right, is there any other part that we're gonna use this mass here? I don't think we're gonna use this mass here, or even the velocity. Is there any part that you're gonna use this velocity? I don't think we're gonna have this velocity in use. All right, I don't think we're gonna have this in use. So let me just remove this part so that we can calculate properly. All right, the power in kilowatt transmitted. All right, we're gonna need that part. All right, let me just write it aside. It's fine. I wanted just a space, which is okay. Okay, no problem. Let me just have it here. Remember I asked to calculate the tensions in this case. All right, that's 6.23. We need to calculate the tensions T1 and T2. And we are supposed to include the centrifugal force, which is TC, is supposed to be included. It must be taken into account. So meaning to say, we are going to be using the formulas that include the centrifugal force, which is TC in this case. In our normal calculation of all our ratios, remember, we just consider for a flat belt. Remember, this is a flat belt that we're talking about. A flat belt in this case. All right, so you're considering a flat belt. If this was not included, which is our centrifugal force, we're going to have the ratio between T1 and T2, which is equal to e to the exponent of micro theta, like that. That was supposed to be our formula. But because we are having now the centrifugal force into consideration, we shall have our formula for the flat belt as T1 minus TC over T2 minus TC, which is our centrifugal force, all right, which is equal to e to the exponent of micro theta, which is the angle of what? The angle of contact. If it was for a V belt, if you are working with a V belt, then you have cosec beta for the groove angle in this. But here we are talking about a flat belt, so not going to have this part. But this formula that we are seeing here, it limits us because we do not have T1 or either T2. Even the centrifugal force, we do not have it. So meaning to say we are going back to the centrifugal force. Where are we going to have this centrifugal force? Remember the formula from our N4, which we said the centrifugal force is the mass, the product of the mass per meter length times the velocity squared. So it's mass times velocity squared. So we're simply going to use the mass. We calculated the mass before. So that's our TC is going to be the mass that we calculated. In this case, gonna have to go back to the information. All right, I think it was aside here. We calculated our mass, which is 15,2. So we are going to have 15,2 here. That's the product of 15,2 times v squared, whereby we are talking about the velocity. Remember V, we calculated velocity here, 30, that was 30,729. All right, 30,729. So we're going to need this velocity. All right, 30,729 squared. That is velocity squared in this case. All right. So we're going to have the centrifugal force, which is going to be 14,000. That was 14,352,92. 59 and so on, which is going to be 926 in Newton in this case. All right. So with this centrifugal force, let us try to formulate more formulas. Yes, we are going to say we now have the centrifugal force. We substitute here, but as you can see, we are limited again, T1 and T2. We are going to be left with two unknown values, T1 and T2. So meaning to say we need to calculate one of these, either T1 or T2, but from where? All right. It follows that from the number of plies that we are given, remember they were given the number of plies and also the maximum allowable tension. We can calculate here the tension of the tight side because we are given the maximum allowable tension. The maximum allowable tension affects the tight side. That's where we are going to talk about this, where the maximum allowable tension is occurring. So from that concept, it means we can calculate the value of T1, which is going to be the product of the width, the number of plies that we are given, and also the the given number of what, which is our FT, which is the maximum allowable tension. Take note, this is taken, we are supposed to consider the units here. It's taken as 6.5 kilonewton per meter width per ply. That's why we are supposed to multiply by the number of what? The number of plies that we are given here. All right, so this is the formula that we're going to use for T1. We are also going to need that T1 here because we've got a lot of unknown values. So T1 from the tight side is going to be the product of the width times the number of plies times the maximum allowable tension in this case. All right, whereby we are going to use, this must correspond per meter or per millimeter. The unit here must correspond to the width. So since it was given per meter, our maximum allowable tension here is given per meter width. We are going to use our width in this case in meters. So our width, remember, the width we talked about it's 1 meter, so it's going to be 1 times the number of plies, which is 4. So we've got 1 times 4. Then also the maximum allowable tension, which is what? 6.5. So that's 1 by 4 by 6.5. All right, so we're going to have the width, which is 1 times the number of plies, 4 times FT, which is 6.5 kilonewton, that's times 10 to the exponent of 3. So this is going to give us T1, which is 26,000 or 26 kilonewton in this case. All right, so that's the value of T1, which is from the tight side. So that means actually we have calculated T1 and it was direct because we also need T1. So we have T1 already. So that means we are just left with T2. And like I said, since we have T1, we can substitute back here to calculate T2. So now we can substitute all the values to find T2. That is T1. We have got T1, which is 26,000. All right, so we are going to have 26,000 in this case minus the centrifugal force. We remember having this into account. So we are going to subtract 14,352,926. All right, everything over the difference of T2 minus TC. Remember, we want to calculate T2. So it will be T2 minus TC, of which our TC is 14,352,926. So this is equal to E to the exponent of the coefficient of friction times the angle of contact in radians. So our coefficient of friction here from this part, remember, from our information, our coefficient of friction is 0.3. So it will be E to the exponent of 0.3 times the angle theta, which is the angle of contact in radians, which is 165 over 57.3. So you're going to have 165 over 57.3. All right, so that's it. We can calculate T2 from there. Remember, we have the value of T1 here, so we are no longer worried about this side. Let us focus on this part to calculate T2. Here, just combine your numerator, guys. These two can be combined together. We can subtract, we obtain 11,647,074. Over here, we can't combine because here we do not have T. So it's just going to remain as it is, 14,352,926. Then on the other side, we can also simplify this from our calculator. E to the exponent of 0.3 times 165 can be simplified, and that gives us a decimal. Let us just try to see what we're going to have from this decimal. That is E, this E here, on this top here, this E. So you're going to have shift E like this, all right, to the exponent of 0.3, right? Let's say, okay, to the exponent of 0.3 times, so you can just have a fraction there, which is 165 over 57.3. That's 57.3 like this, right? Which will be 2.3723, something like that, which is 2.372. So you're going to have 2.372 like that. All right, this is same as over 1, so that we can simply cross multiply because we're now dealing with the normal equation. So we can just cross multiply so that we can have the value of T2. So that's 1 times this value which is 11647,074. Then you multiply, so you're going to multiply this value here to T2. Then you also multiply to this value here. All right, so if we multiply 2 times T2, it's going to be 2,372 T2 in this case. Then we multiply this value and this value together. Going to multiply these two values. So that is going to be a negative 34,000. So it's going to be 045. So that's 045, 1407, 1,4. So it's going to be 14 there because there is a zero at the at another part. There is 14047. So you're supposed to have a zero here, which is just going to remain like that. So to find T2, you can transpose the negative value here to the left-hand side so that it can be positive. So here we are going to add this value. On this side, we are going to add the value. So that will be 45,692,214, which is equal to 2,372 T2 in this case. All right, so this is going to give us the value of T2. If we divide by this value both sides, we are going to obtain the value of T2 as 19,263,15936, something like that, which is 159 in Newton. All right, so that is it. We have got the value of T2 in this case. So that was the question, to find the values or to find the tensions, which is T1 and T2. So including the centrifugal force and also considering that this is a flat belt. So the formula that you're supposed to use must correspond to what you're dealing with. All right. Then the other part, they need us to calculate the power in kilowatts transmitted by a 1 meter belt width in this case. Remember, we calculated the velocity and we also calculated T1 and T2. So you can use the effective tension because we've got T1 and T2, which was being calculated at 1 meter. All these values, they corresponded at 1 meter belt width. So meaning to say there's nothing that we're going to change in this case. All right, 6.24. So remember, power is the effective tension times the velocity, which is T1 minus T2 times the velocity. So we've got T1 here, 26,000 minus T2, which is 19,263. All right, 159. All right, then we're going to multiply to the velocity that we calculated here, which is 30,729 in meters per second. So this is going to give us the transmitted power, which is the output power. That was going to be 207,216,3871, which is something like that, 3871, something like that. All right, you can even convert to kilowatts, guys, because yeah, it's too much. All right, just convert, divide by 1,000. It's going to be 207,016 in kilowatts. All right, so it's being taken per what? Per meter belt length in the belt width in this case. All right, per transmitted by 1 meter belt width. So we can just present this as per meter belt width. All right, so that's it. Got 2 marks for that. All right, so this is how some of these questions might be given as. Then we've got the actual belt width in millimeters. All right, now they want us to calculate the actual belt width in millimeters. So remember, we calculated the power that is transmitted by the belt. And we have the actual power in this case, which is 65 kilowatt, which is the power transmitted. There's power transmitted before, and there's power transmitted due to the width. So this can give us the actual width. So the actual width is simply going to be given by the formula, the power over the power per watt, the power per meter. All right, let me just write it here. This is all right, this is 6.25. So 6.25, the actual width of the belt is going to be taken from the total power in this case, that is the total power over the power per meter belt width, right? Over the power per meter belt width in this case. All right, remember, we calculated power from the information that we are given that we had before. So you can just apply that. Okay, this is our power in kilowatts, which is 65 kilowatts. That is the total power transmitted before, which is 65 kilowatts. Remember, the power here was also in kilowatt, but kilowatt per meter. So I'm just gonna use this is kilowatt. Sorry, guys. All right. Then the power that we calculated here, that is transmitted per belt width in this case, which is this one, per belt width, we calculated this value here. We got 207,06. So let me just remove this, but I just need the answer here. So we calculated this and got 207. And take note about the units there. This is 207,016, which is in kilowatt per meter. So this is going to give us the actual width if we simplify this. As we can see, the kilowatt and the kilowatt will cancel, and our answer is going to be left 1 over 1 over like this meter. So our answer is going to be in meters. So that will be 0.3139852, something like that in meters. But they say this must be in millimeters, so just multiply by 1,000. Your answer to be in millimeters, you're going to obtain 313,985, which is in millimeters. So let us just say if you have this like the actual we are talking about the belt width, like the exact width, you can just round off to the nearest whole number, which can approximate to 314 millimeters. All right, these are millimeters we have converted to millimeters. All right, so it can just approximate to 314. That is approximating to the nearest whole number. All right, so guys, this is what we can see, and it's just a matter of you knowing your formulas here. This is a matter of you and your formulas. Work with the formulas, revise also from your N4, just take some information from there. Our formulas, they are simply one and the same from what we did in N4. So it's just need us to perfect our formulas and also to consider adjustments whereby we are given the density of the material, this and that, and the angle of rep, which is representing in this case, which was representing the angle of contact. And whenever you're dealing with the angle of contact for a flat belt, you talk about a flat belt. Whenever, whether we are dealing with which part, as long as you talk about the angle of contact, it must be in radians. And also this concept of that we are given that it's a 4-ply leather belt. So meaning to say that we are talking about a flat belt in this case, okay? If it is a V belt, you're going to be given as the number of V belts in this case. The moment they give you that, you know that, okay, I'm dealing with a V belt. So that's how our questions will be given.